Good afternoon. I just recorded about 5 minutes of this video already and realized that my microphone was muted, and so you couldn't hear anything that I was saying. So I get to start all over again and say all of the things that I already said just now. One of the first things that I said was that this video may be broken down into two parts because I feel like my voice is starting to get a little scratchy. And now that I've talked for 5 minutes for no reason, it's probably going to be even worse. So I'll try and get as far as I can. If I have to stop, I will pick back up again where I left off and just make a second video. But this video is going to cover at least part of the last section in Unit 2, which is Section 1.8, Rational Expressions and Equations and Radical Equations. We are going to begin our discussion with rational expressions. And I actually am going to skip over this part about domain because I feel like it's more applicable when we start talking about equation stuff. And so I'd rather relate it to that in that way than begin with it and have to refer back to it. So I'm going to kind of just scroll down here a little bit and see that again a little bit later. So I'm going to start with simplifying, multiplying, and dividing. These are the most basic of the operations that you're going to be dealing with when dealing with rational expressions. Now, rational expressions are technically just fractions containing algebraic expressions. So you can see an example of one right here. This number 1 here is a rational expression. It's an algebraic fraction. Now, just like regular fractions, algebraic fractions can be simplified if they contain any common factors. The difference is that you have to be very careful and specific when you are going through and trying to find common factors. So when we begin our process for all three of these things, we're going to start at the same place, and that is factoring the polynomials completely. We have to see what they're made of in order to determine if they have anything in common. Also, important side note, when you are deciding whether or not you can simplify, monomial expressions simplify with other monomial expressions in whatever way works best for them. So you pull out whatever common factors they have and get rid of them. However, binomial factors can only be simplified if there is an identical matching factor on the opposite side of the fraction bar. And what I mean by that is if you have an x plus 7 on the top, the only way that you can cancel it out is if you see an x plus 7 in the bottom. You cannot cancel x plus 7 with x minus 7. You can't cancel x plus 7 with x minus 4. You can't do any cancellation of binomials unless they match entirely. And then the entire thing cancels out. So that's just a couple things to keep in mind whenever you are going through and doing this simplifying. Same rules apply for multiplication and division. So we're basically going to be following the same rules for these three operations. So to check this out and see how it works, I'm going to begin with this polynomial expression, 6n squared plus 6n minus 72, and 3n squared plus 6n minus 45. Now, I am not allowed to consider these things together at this point because right now these are two completely different trinomials. Even though they have some stuff that looks similar, you cannot cancel any pieces out of a polynomial. You can only cancel pieces out of monomials. So we have to begin by factoring. So we're going to factor out, first of all, the GCF, 6 on top. I'm left with n squared plus n minus 12. Oh my gosh. And on the bottom, we factor out a 3, and I'm left with n squared plus 2n minus 15. So these are some monomial stuff on the outside, and we might be able to cancel some stuff, but we're not going to look at that yet. I like to get these things in complete factored form before I do anything else with them. So I'm going to take both of these trinomials one step further because both of them factor further. And on top, n squared plus n minus 12 factors into n plus 4, n minus 3. On the bottom, n squared plus 2n minus 15 factors into n plus 5, n minus 3. Remember, the order that you put these things in doesn't matter. Typically, we put the monomials out front, but the binomial stuff doesn't make a difference. So this is complete factored form. Once your trinomials have been completely factored, now we want to take a look at what's going on in the top and bottom. Remember, if you have monomial pieces here, you can simplify those in whichever way is appropriate. In this case, 6 divides by 3 evenly, so the 3 is going to go entirely and the 6 will become a 2. Once you deal with any monomials, you want to look through and see if you have any identical binomial factors. And if you have any identical binomial factors, you want to cancel them out. In this case, n minus 3 is identical, so they cancel each other out. Now, once all of the common factors have been removed, anything that's left over, you just write where it is. You don't have to multiply it back out unless you really want to. You don't have to do the distribution or the FOILing or anything. You're not actually going to be multiplying any of these. You're just going to write them next to each other. So, for example, left over on top, I have a 2 and also an n plus 4. And I can write them next to each other just like that. And on the bottom, I have an n plus 5, and there's nothing else down there. Now, if you really want to, you can distribute that 2 through, but it is not necessary. You can leave these in factored form for your final answer. So for simplifying, you're going to break down everything as far as you can, see what they have in common, and get rid of it. Multiplying and dividing follow the same suit. They both just add in one extra piece. If you look at a multiplication problems look similar to the one that we simplified, except that there are 2 rational expressions instead of just 1. Now, I want to remind you of the rules about multiplying regular fractions because it's helpful when dealing with these rational expressions. When you are multiplying these regular, when you're multiplying regular fractions, I completely lost my train of thought. You're allowed to cancel before you actually do any multiplication. You can cancel within the same fraction, so top to bottom within the same one. You can also cancel across on the diagonal, which is called cross canceling. And all of this can be done to simplify your expression before any operation is actually done. And when we're working with these rational expressions, we're not going to be doing this multiplication anyway. We're going to simplify as much as possible, and then anything that's left we'll just write next to each other. So you don't have to do the multiplication. We still begin this by factoring. So it doesn't really matter what operation's happening, you're still going to factor everything completely. So for example, in the top left here, the only thing that I can do is factor out a GCF, which is n squared. I have n squared on the outside, and when I factor it out, I'm left with n plus 2. On the bottom, that's a difference of squares. It factors into n plus 2, n minus 2. That looks like an H, but it's an N. times. The top right is a type A trinomial. It factors into n minus 3, n minus 2. And this bottom expression down here actually has the greatest common factor that's going to pull out first. So I'm going to take out the GCF, which is 4n. It leaves me with n squared minus 4n minus 12. Excuse me. And now this is going to factor further. So I have a 4n in the front. And then this guy factors even further into n minus 6, n plus 2. Some of these look like h's. All of those are n's. It's just this pen. I'm not real good at drawing with this pen, but I'm trying. All right, now we have a bunch of stuff in the top here and a bunch of stuff in the bottom. We can cancel anything in the top with any one matcher in the bottom. Now, I said one because it's one-to-one cancellation. One thing on top cancels one thing on the bottom. You can't just take one thing on top and 5 things on the bottom. It doesn't work that way. So it's one-to-one. Excuse me. For example, I have matching binomials n plus 2. And whether you take this one out or this one out, there's still going to be one left. So it doesn't matter which one you take. We also have matching binomials n minus 2. And then we have some monomial stuff, the 4n and the n squared. Remember, you could take whatever you need to out of those. You could take pieces. So for example, the n cancels here, and I'm just going to take that square away because I took one of the n's out. Now that's everything that we can take. All the monomial stuff that we can is gone. All the matching binomials are gone. So let's just write what left. Left on top is n and also n minus 3. Left on the bottom is n minus 6 and also n plus 2. Again, it is unnecessary to multiply that stuff out. You can just leave it in factored form written next to each other, and that's just fine. So multiplying takes the simplifying and just goes like one little extra bit. Division builds on multiplication. So the multiplication stuff is the same, except there's one extra rule here as well. So I want to come off to the side here and discuss this little rule about dividing fractions. So when you divide fractions, a over b divided by c over d. This expression cannot be performed in this manner. When you divide two fractions, you're not dividing at all. You're actually multiplying by the reciprocal of the second fraction, which means this expression can be rewritten as a over b times d over c. Keep the first one, change the division to multiplication, and flip the second one over. So we're going to follow this rule whenever we go to do these expressions as well. And we are going to, they say keep it, change it, flip it. It's really multiplying by the reciprocal. And so we're dealing with this problem here. And I like to factor and do the keep, change, flip at the same time just to save some time. That's a personal choice. You do not have to do it that way. But as long as you flip the second one, it doesn't matter if you do it first or do it second. It makes no difference. I just think it saves time if you do both steps at one time. So I'm going to start by factoring this trinomial here. And that trinomial right there is a type C trinomial. And we did type C trinomials with the bottoms up method, which means that I am beginning with multiplying 2 times negative 12, and then finding factors of this value, negative 24, that subtract to give me 5. And that would be positive 8 and negative 3. Now, in bottoms up, we begin our parentheses with those two factors, but we don't stop there because we have to bring back in that leading coefficient. In this case, the leading coefficient is 2, so we're going to divide both of these factors by 2. And then remember, we're trying to find simplified form if we can. And if we cannot, we are going to bottoms up the denominator into the front of its respective parentheses. So this first fraction does not simplify, negative 3 over 2. So we're going to bottoms up and make this 2x minus 3. The second parenthesis does simplify because 8 divided by 2 is just 4. So x plus 4. So there's your top. The bottom has a GCF of 5n. I'm using x's. I got to keep with x's. I'm not fixing that. Okay, so we're going to factor out a 5x. I know it's supposed to be n's. I'm sorry, I just noticed. We're left with x minus 4. And now here's where the change and the flip come in. Change the division to multiplication and flip this guy over, which means that my new numerator is going to be this difference of squares right here. And that factors into n minus 4. Sorry, I'm using x's. X minus 4, x plus 4. The bottom now is this guy here, and it looks like we have a GCF of 10n. So 10n, crap, I'm using x's, 10x, and then I'm left with 2x minus 3. All right, so I did the keep it, change it, flip it, and factored it all in one fell swoop, so now it's done. So once again, I'm left with a multiplication problem where everything is in factored form. And I want to go through and see if I can cancel anything out and simplify this thing a bit before I try to put them back together. So we're looking top to bottom. On top, I have a 2x minus 3 that will cancel this one. Looks like I have x minus 4 that will cancel. Notice I have matching x plus 4s here, but they are on the same level. And if they're on the same level, they don't cancel. So you have to keep both of them. And you can write both of them next to each other, or you can write one of them with a square on the outside. Either way is fine. And on the bottom, I'm left with 5x times 10x. Now, normally in the past of these, we haven't multiplied these pieces together. We just wrote them next to each other. But 5x, 10x would look weird. So as a general rule, if you have monomial pieces left, actually multiply them so it doesn't look ridiculous, because it will look stupid if you don't multiply them together. Plus, it's really easy and fast to multiply monomials. 5x times 10x is 50x squared. And there you go. So simplifying, multiplying, and dividing basically all kind of follow the same rules. It's just that some of them are a tiny bit more in depth than others, and that's okay. It's still the same concept. Factor and cancel as much as you possibly can. Now, adding and subtracting. Oh, I forgot this guy right here. Geez, sorry. Well, you know what? There's adding and subtracting in here, so I'm going to come back to this because I want to talk about how to deal with algebraic fractions anyway. And so let's talk about the adding and subtracting real quick first. So here are some steps and information about the adding and subtracting when we're dealing with rational expressions. First of all, just like regular fractions, you absolutely have to have a common denominator. You cannot add or subtract any type of fraction without having an LCD. So what we want to do is figure out what the LCD is supposed to be. And there are a couple little tricks that you can do to find what the LCD is going to be in your expressions. The biggest thing is to factor the denominators if it's possible so that you can see what they're actually made up of. Because if you don't know what they have, you can't tell what you have and what you need. So it's best to start with the factoring and see what you've got. Now, this part of it to me is a bit confusing. Yes, it works if you're dealing with monomials, but when you're talking about binomial expressions, I like to talk about them in terms of what they have in common and what they don't. So I'm going to just kind of scribble this out. When you're dealing with monomial variable expressions, then sure, take a look at what you have, find the LCD for any coefficients, take the highest power on your variable, and that will be how you deal with monomials. However, for binomials, you want to take one of any common factors and all of the uncommon factors. So if you see something that they have in common, take it. But you only need one to account for it. If you see stuff that they don't have in common, you have to take all of that. Every single thing has to be accounted for in one way or another, whether it's common or uncommon. So that's the general rule of thumb for finding the LCD. Once you have your LCD, you want to compare your current denominators to what the LCD is supposed to be. And anything that they are missing, you will have to bring in and multiply top and bottom by that value. Now, when I say multiply, I mean actually multiply on top. It's more like multiplying quotations for the bottom, because on the bottom, you're not going to multiply, you're just going to put them next to each other. So you'll multiply out these tops and get these things spread out in usually foiled form, but a lot of times it's distributed as well. It just kind of depends. And then once you have all these things multiplied out, you're going to combine like terms. When it says right here, be careful of your signs, that's because if it's subtraction in the middle, you have to change the signs on the right of the subtraction symbol. Only in the numerator, but still it's required to change all those signs. But you'll combine all the like terms and get this thing simplified. Then at least it's all put together over a single denominator. And if you could factor and simplify, you would. Sometimes you can, sometimes you can't. It just depends. So this example up here above these notes is called a complex fraction. And in a complex fraction, you're actually looking at a division problem. It's just written in a different way. This problem right here is the same thing as saying 3 over x plus x over 3 divided by 2, I'm going to put it over a 1, minus 1 over x. That means the same thing. It is a division problem. It's just written in complex fraction form. Now, the problem with this division problem is that your numerator and denominator are not combined like they were in the last one. You have separate pieces that do not currently have a common denominator. Now, these are monomials, so it is a little bit easier to deal with than it would be if it were binomial expressions. But we have to kind of see what we've got and what we need. So, for example, in this expression on the left, we've got one denominator that's an x and one that's a 3. X and 3 are monomials, and they don't have anything in common, which means that the LCD on this side takes both of those pieces, 3 and x. Now, if I know what it's supposed to be, I can tell what's missing from each one. For example, the first one only has an x. We need a 3x, so we're going to bring in a 3. The one on the right has a 3. It misses the x, so we bring it in. Now, we are looking at 9 over 3x plus x squared over 3x. When we go to combine these two things together with addition, there aren't any like terms in the numerator, so really the only thing we're going to be able to do is write these two things next to each other. Remember, the rule for adding and subtracting fractions is that the LCD stays the same. You do not add or subtract the denominator. It remains whatever you made it. So there's my first expression, 9 plus x squared divided by 3x. On the other side, we have to do something similar because we've got to find a common denominator again. This time, my denominator on the left is a 1. Denominator on the right is an x. If one of the denominators is a 1, that means the LCD is the other denominator, which makes this side a little bit easier. The expression on the left here needs the x, but the one on the right doesn't need anything. So we're looking at 2x over x minus 1 over x. And now in similar fashion, we can't really combine those numerators, so we just write them next to each other. 2x minus 1 over x. Now this is a nice little division problem that we have created by combining all this stuff together and making it look nice and neat. And so now we can do the keep it, change it, flip it. Multiply by the reciprocal. The first expression stays, 9 plus x squared over 3x. The division changes to multiplication. And this second guy here flips over and becomes x over 2x minus 1. This binomial expression is not factorable, and neither is this one. So we're really not going to be able to do a whole lot of simplifying, and we definitely can't do anything with these two binomials. So I want to draw your attention to the monomial pieces across on the other diagonal, because at least they have an x in common that can go away. That means that on top, all I have left is 9 plus x squared. And on the bottom, I have a 3 on one side and a 2x minus 1 on the other. No, you cannot simplify the 9 with the 3. 9 is part of a binomial and 3 is a monomial. So they cannot cancel each other. These two pieces are stuck together. This guy is by himself. So we're not allowed to take pieces out. All right, let's go down. I want to go all the way down. I want to go past this one because I don't like it. I want to go here. So these have more going on in them, and that's why I want to come here. So excuse me. So we have a subtraction problem here, and we have a subtraction problem here. That's fine. Subtraction just means change the signs on the right once you get there. If it was addition, we would leave everything alone. Subtraction is actually better to see because it's the one that people tend to get confused on because you have to change those signs. But with addition, you don't have to worry about that. You just combine everything as it is. In these two different problems, we have denominators that can be simplified. And so we definitely want to begin by getting both of these denominators in factored form so that we can see what they're made of, and that way we can tell what they have in common and what they don't. So I'm going to start by factoring the left-hand side. Factors of 16 that add to give you 8 are 4 and 4, both negative. So we've got x minus 4, x minus 4. On the other side, factors of 4 that subtract to give you 3 are 4 and 1. 4 will have to take a minus, and the 1 will take a plus. Now, these two things are factored, and we can take a look at them and see if they have any common factors and any uncommon factors. So I want to begin by looking for common factors. And if you take a look here, we've got an x minus 4 on this side and an x minus 4 on this side. Now, I know the other side has 2 of them, but you're only allowed to do one-to-one comparison. So if I have one factor in common, taking an x minus 4 accounts for that one common factor. So our LCD begins with the common factor, x minus 4. That looks like a 9. There. Now, once you remove the common factors, you want to look and see what's left, because anything that's left over that is not a common factor has to also be taken. So in this case, I have another x minus 4, so I got to take that. And I also have an x plus 1, so I take that. All right, so all three of these pieces combined make up my least common denominator. And you'll notice that each one of these denominators on their own only has 2 pieces, which means that there's something missing on both sides here. And we want to go ahead and bring in that missing piece on both sides. So on the left-hand side, I have both of the x minus 4s. I need to bring in the x plus 1. X plus 1, x plus 1. On the right-hand side, you can see that you have one of the x minus 4s and the x plus 1, which means over there I have to bring in the other x minus 4. Oh, bottom 2, x minus 4. Now, once you have all of the required pieces in the denominator is locked. It's done. So you don't really even have to work with the denominator anymore. It is done. Leave it there. And now let's work in the numerator. We'll bring the denominator back at the end. So the numerator right now looks like this. 9x times x plus 1 minus 7x times x minus 4. Now, if we write it like this, it's pretty easy to simplify this top expression. You see that you have some parentheses, which means we're going to have to distribute. So let's pick up our blue and we'll distribute in. 9x times x is 9x squared. 9x times 1 is 9x. The minus in the middle will kind of attach itself to this 7x, so the sign change will happen naturally. Negative 7x times x is negative 7x squared. Negative 7x times negative 4 is positive 28x. Now, this is the numerator in its entirety. We can now combine like terms in that numerator and get it in simplest form. 9x squared minus 7x squared is 2x squareds. 9x and 28x is 37x. And that's our simplest form numerator. So throw the denominator back on there. X plus 1, x minus 4, x minus 4. The order that you put the denominator in does not matter. Multiplication is commutative, so order's fine however you want it. Also, a lot of people like to shorten this and write it as parentheses x minus 4 squared, which is fine as well. It's whatever you're comfortable with. And a lot of people like it that way best because it's a little bit shorter, which is fine. Now, important side note, I just want to mention this. So I'm going to come off to the side. The numerator of this expression is factorable a little bit. And x would come out and you'd be left with 2x plus 37. The reason why I wanted to come off to the side and do this is because if you look at this in factored form, nothing here is going to cancel anything on the bottom. So when you get into a situation where your numerator is factorable but won't actually do anything, then it's not necessary to actually go through with the factoring. You can if you want to, but it's just not something that has to be done. If it doesn't help you cancel, I wouldn't waste the time doing it. So this is good for your final answer. However, though, if you want to factor it and put it like that, that's fine too. I just don't usually spend the time doing that if it's not going to help me. All right, so hopefully the step-by-step is helping kind of grasp what you're going to do with these, because it is quite a few steps to get us to where we need to be. And a lot of them are similar between the different types of expressions that we have. So it's very important to make sure that you practice doing this stuff so that whenever you get these different types, you know where you need to go for each one. Because there is a lot of factoring involved, but then you do different things afterwards. So I would definitely recommend practicing as much as you can. Let's take a look at this third one here. Whoa, too far. There we go. Still too far. I don't like that. Okay. So we're going to do some similar operations here, just with these new polynomials that are here. So let's pull up some other colors. Let's use purple. We're going to factor these denominators completely. First off, on the left-hand side, there's a GCF of 2, and then I'm left with n squared minus 16. And that is the difference of squares, which factors further. So actually, this is going to look like 2 n plus 4. That looks like a 9. I'm really sick of that happening. N plus 4 n minus 4. And now on this side, we have a GCF of 3, which leaves me with n squared minus 5n plus 4. And this trinomial factors further into n minus 4, n plus, nope, minus 1. So here's my complete factored form of my denominators. Now when I'm finding my LCD, typically I begin with finding the common factor. So I'm going to get my little highlighter out again, and I'm going to go through and find my common factor between the two. Is there anything in common from one side to the other? Well, I see a common factor in minus 4. One right here, and I see one right here as well. So that means I take one of those common factors. So for my LCD, I begin with the n minus 4. Now, what's left over after that is monomial pieces and binomial pieces, and they're treated differently. Monomial pieces are treated just like you would if you had regular fractions. We have a 2 and a 3. What's the least common multiple for 2 and 3? And that's going to be 6. I'm going to tack that at the front so it looks right. For the binomial stuff, whatever they don't have in common, you take all of it. So I have to take an n plus 4 from the left, and I have to take an n minus 1 from the right. So that's my whole LCD. Now when I go through and try to compare denominators with the LCD, the monomial pieces get compared together and the binomial pieces get compared. So I begin with the 2 and comparing it to the 6. To make a 2 into a 6, I need to bring in a 3. Also, I am missing one of the binomial pieces from the LCD. I have the plus 4 and the minus 4. I am missing the n minus 1. That's hard to read. On the right-hand side, I do something similar, except this time I have a 3. So I'm comparing a 3 with the 6, and I need to bring in a 2. And for the binomials, I have the minus 4 and the minus 1. So these two here, I'm missing, nope, these two here. I'm missing the plus 4 in the middle, so let's bring that as well. So now we can see that both of my denominators have all the pieces they need. We've got a 6 out front, and plus 4, and minus 4, and minus 1. Same thing here, 6 out front, and minus 4, and minus 1, and plus 4. The order doesn't matter as long as it's all there. So now the LCD is locked. We are ready to go with the numerator. So I'm going to work with the numerator now. And it looks like on the top left, I have 7 times 3 times n minus 1. So I'm going to make that a little bit nicer and write it as 21 times n minus 1. And then minus 9 times 2, so 18 times n plus 4. That at least makes it look a little bit nicer. Also, it puts us in the same situation we were in last time where we have the sign right here, and if we do our distribution with it, it will solve its own problem of changing the signs. So I distribute 21 times n, 21n. 21 times negative 1, negative 21. Negative 18 times n, negative 18n. I don't know what that is. 18 times 4. Negative 18 times 4, is negative 72. So here's all of the numerator multiplied out. Now I just need to go back through and combine like terms. Get everything kind of condensed and nice and neat, and we'll put them all together. So we are looking at, if I combine, 21n and negative 18n, that gives me 3n. And negative 21 minus 72 more is going to give me negative 93. And now that's my numerator all done. I'm going to come over here to the side and put it all together. This is 3n minus 93 all over 6n minus 4, n plus 4, n minus 1. Now, I want to point out here that this time, factoring in the numerator will help you simplify. This numerator here factors. A 3 factors out, and I'm left with n minus 31. Now, it wouldn't be that big of a deal, except that we have a monomial on the bottom as well. And that monomial on the bottom is a 6, and 3 and 6 simplify. 3 goes, 6 becomes a 2. Even something that small has to be done in order for this thing to be considered simplest form. So if I divide the 3 out, I'm left with n minus 31 on top, and on the bottom, I now have a 2 in front, but all the monomial stuff is the same. N minus 4, n plus 4, n minus 1. And that is your final simplest possible form answer. If you do not go that extra step to simplify, you will not get full credit because your answer will not be in simplified form. And I think in Hawks it says that your answer is correct, but it's not simplified. So you want to make sure that if you go through all this work to get all of this stuff, that you go that extra step to make sure it's as simplified as possible. If it can't be simplified, then that's fine. Sometimes they can't be, but if it can be, it has to be. All right, so the next little part is rational equations. I think this would be a good place to stop since we did all the expression stuff. And then the next video will start with domain, and then the rational equations, and then the radical equations so that you can see them. So the next one will be kind of like the solving stuff, and this one was just the simplifying stuff. So I'll probably do that one tomorrow and get it posted tomorrow afternoon. But for now, this should get you through at least part of it because a lot of it is going to be this expression stuff. So check back again tomorrow and we'll get the rest of this stuff taken care of. All right. Have a good day.